All right, I think we are on again. So, for this question, we are talking about directed graphs. So there's actually a question on your quiz that involves directed graphs and relations concerning them. And so I want to, one, explain what directed graphs are, so that way you're more familiar with them before you talk about them, but also how to find relations between them. Okay? So here I have two directed graphs. Okay? This one and this small one, this big one and this small one. All right? One of these is an equivalence relation, and the other one is not. And I'm going to show you how to find out how you know which one's an equivalence relation. Okay? So we are going to define a relation. We're going to let R be the relation. This is relation right here, where X is related to Y if and only if there is a directed path containing X and Y. Okay? So in the context of graphs, okay, graphs are just points and dots. Okay? So here's a point right here, here's a point right here, here's a point right here, here's a point right here. Okay? So just lines and dots is what graphs are. So you may have heard these if you took a class called graph theory. Neural networks, all different kinds of applications are done with graphs. If you took maybe discrete mathematics, you may have talked about graphs a little bit. But these are directed graphs. They're directed because they go a direction. So here, this A goes to B. So this arrow is showing its direction. Okay? And this B also goes to A. Now, this A also circles back on itself. This B circles back on itself. That's supposed to be labeled D right here. Apologize for that. This D goes to A, etc. Okay, so, and this one is the same. You have A goes to A goes to D, all the like. Okay, so question, which one of these is an equivalence relation? Okay, so what we are going to do is we are going to try and find out which one of these is an equivalence relation. So how do we do that? Okay, well, for something to be an equivalence relation, we have to have what's called symmetry. Okay, so in this case, we have to have called, well, it has to be reflexive first. Let's say reflexive, which means that X is related to X. Okay, I said X is related to Y. That's not true. It's reflexive if X is related to X. Okay? It is also symmetric if X relates to Y implies that Y relates to X. Okay? So you're kind of given X is related to Y, so you want to find, okay, does that mean Y is related to X? And it's transitive. Transitive. So X is related to Y. You're given X is related to Y. Y is related to Z. So you want to show then that X is related to Z. Okay? So all that is what you're trying to find. So how the heck do you do that with graphs? Well, we define our relation to be, we say X is related to Y if there's a directed path from X to Y. So if there's a path, okay? So let's look at that. Let's see. Let me just put a little box around this. That way, you know, this is separated off and I can do all my work in this slice, right? Okay. So what we see, we want to see, okay, are all the dots related to, are all the nodes related to each other? So is there a path from each node to itself? So here we see that AA is in the relation. Oh no, let me move this down. Let me move this down real quick. There we go. That's as far down as I can move it. So we see that A is in the relation. Why? Because A relates to itself, right? It loops back to itself. There's a path from A to A. Well, that also means that BB, what else? That relates to itself. C relates to itself, so CC. And what else? DD. These are all in the relation. Okay? So, hence, this is reflexive. Okay? This is reflexive. Now, we see that AB and BA is in R, right? Because A goes to B and B goes to A. We also see, what else do we see? We see a lot. We see that A goes to D, and D goes to A. That's also in R. We also see that D goes to C, and C also goes to D. Those are both in R. And B goes to C, and also C goes to B is in R. Okay? So, everything that goes to one point also goes to the other point. Okay? So, symmetric. So this is a symmetric relationship. However, it's not transitive, actually, because, however, A goes to B, right? And B goes to C are both in R, but, so A goes to B, B goes to C, but does A go to C? Is there an A that goes to C? No, there's not. Okay? AC is not in the relation. Okay? It's not in the relation. So, because it is not transitive, also, it is not an equivalence relation. Okay? So, not equivalence relation. I'll get out of the way so that way you can see the whole thing. So this graph, although it is beautiful, is not an equivalence relation. Okay? Now, let's look at this one. Let's see if we can do this one. So here, A goes to A, B goes to B, C goes to C, and D goes to D. So we have AA, BB, CC, and DD. These are all in the relation. Okay? All those are in the relation, so reflexive. Okay? What else do we see? Also, we see that AD, A goes to D, but also DA is in the relation. And what else? We see that BC, but also CB is in the relation. Okay? All of that is in the relation. And there's nothing else, right? So we don't have to write A goes to D and B goes to A, because that doesn't happen. Okay? So this is symmetric. Okay? So this is symmetric. All right? And also, it's transitive. Okay? So what we can do here to prove transitivity is we can partition the set S into A, B, C, D, okay, into the blocks determined by every element by AD and BC, okay? All right, so within that block, okay, follow me here. Proving transitivity with graphs is actually kind of difficult. There's a whole course on it, just called Discrete Math 2. It's a whole chapter, but this is like a simpler way of saying it, okay? So within each block, every element is related to every other element in it, right? Okay. Therefore, for any x, y, z in the block, if x is related to y and y is related to z, then this is dying. Let me say this. If x is related to y, y is related to z, then x is related to z. Okay? And the equivalence classes, okay, let me go over here for that. The equivalent class of A is everything that's related to A, but that is equal to the equivalence class of B, right? That is equal to the equivalence class of B, which is just the set AB. And also the equivalence class of B here is equal to the that would be D. I'm sorry, y'all. AD and BC are equal to each other, which is just the set of containing BC. Okay? All right. So, this is the proof. It's a lot, I know. But this should give you some intuition on how to find it. Okay? So, not all sets are going to be like this one, okay? So the biggest thing is for transitivity, what you're trying to show is that if x is related to y and y is related to z, then a is related to z, okay? But what we did was we created these blocks here, okay? Everything in AD and everything in BC, right? And we said, well, of course, everything then is related to itself, okay? All right, so that's how we do that one, all right? And I will make a new video in one moment.